Okay, now I'll just stop you there for the moment, and while we consider drawing these force vectors, and rather than trying to draw a person, I've just drawn a circle. It's much easier, and you can waste a lot of time in a test or an exam trying to draw, artistically, when you're not going to be assessed on that. The general rule of drawing force vectors is that it should begin, so the tail should be at the centre of the object. So if I'm drawing my weight force, then I'm drawing it from the middle of the object and it's pointing down. I could also be representing this as gravitational force, whatever. I could be using just a capital W. But as long as it's clear what you're indicating, any of those sorts of abbreviations are acceptable. So I could just say this is a capital W for weight. I could have a lowercase g there to indicate that it's a gravitational force. But if this is when the person first leaves the aircraft, remember they had no initial velocity. So the only force acting is the weight force. There's no other forces. And if we think about, well, in the first couple of seconds after they leave the aircraft, the important thing is to make sure that the weight vector is identical for each time you draw it. It wants to have the same length. We're not measuring it, but we're making sure that we're consistent across our diagram. And so our force due to air resistance or drag or whatever is starting to be obvious. So let's say this is about 3 seconds. And then if we're talking about terminal velocity, the important thing here is that these vectors must be the same length. These must be the same length, because what we're trying to indicate is that they are balanced. This one can't get any smaller. This one's the same all the time, because it's a function of the mass of the object. Yeah, and its acceleration, and so this vector doesn't change in size. But this one is changing in size because we said as the object accelerates, it's going to encounter more air particles, and so it's going to that's going to increase the force opposing the motion. Does that make sense, or is anybody not sure about what we're trying to do here? Now, if we opened our parachute, we still have the weight force is still the same, but in actual fact, we are going to be slower, aren't we? We've got another force acting up, don't we? We have the drag from the parachute as well as air resistance. Does that make sense? That if we looked at how this is going to be moving faster over here, and then this one will be here. Okay, so this is faster, and this is slower, because, yep.
What's the difference between drag and air resistance?
Well, nothing.
Okay.
Nothing. I'm just representing that to show that this is from the parachute.
Okay. So could you write that as just one vector?
Yes, absolutely.
Okay.
But this is why it's slower, is because we've got those, we've effectively got, we've increased the drag.
So relative to the last air resistance vector, how, like those two together, they'd be bigger?
These, when we open our parachute, those two are going to be bigger than this one. So, but they're still going to be smaller than that one. What if we leave that? Something like that. Because we're still moving downwards, aren't we? We're still accelerating towards the ground, because what I'm not representing here is terminal velocity again. Because terminal velocity will look like that when. Yeah? Does that make sense that what we've done is we've increased the drag or the air resistance by opening the parachute? We could represent that as one vector, and the one vector would be bigger than that.
Wait, so your last one, it's in between those two, so it's not going to be as.
So this, if we're thinking about, we left the aircraft, there was only the one force, then air resistance grows and grows and grows as we accelerate until it is equal to the weight force. But then if we open the parachute, then we increase the drag force, and relative to the size of the air resistance it was before, and so we're going to end up slowing down.
Surely air resistance would be bigger because there's more surface area. Oh, hang on. No, that's what you said before, Brett, wasn't it? So you've got drag and air resistance are the same thing. It's just.
That's right. They're the same thing. And they, if this is actually going to be quite large. We're not going to move up, but we're going to slow down, so we're decelerating.
So we're increasing the surface area, which means that we need more. I'm trying to visualize it.
So, what? You just have the one thing. Drag and air resistance are the same thing. Just have
Well, we can just have air resistance if you like,
and then that would just be real big.
and then let's do that then, because it seems like otherwise it's confusing.
So is the air resistance bigger or smaller?
It is going to, the total will be bigger because we're now decelerating, which means we are accelerating in the negative direction. But we're not going to change direction of our motion. We're just going to slow down. Does that make sense?
Yeah.
Is that better with just the one?
So hypothetically, how much would it take for us to turn around? Like, is that possible?
Well, no. As in to start to take off and fly up.
Yeah. So with our forces, we've got, like, when movement is caused by like unbalanced forces, and so they're unbalanced,
That's right.
and
At this
the air
point, they're
resistance is
unbalanced.
larger than the sort of the force downwards. So if you were to look at that, you would probably think that it'd be going up because there's more upwards force, but it's not. So why is that?
It's because, remember when we thought about hitting a ball with a paddle, you know, with it attached to an elastic band, that the motion can still be away even if the force is going to be is growing to pull it back. Or tossing the ball up in the air, the force is down. The gravitational force is down even though the motion is up. But it's up, but it's slowing down.
Okay.
And it's the same sort of thinking here, is that the force is up, causing it to slow down, but it's not going to slow down enough to stop and then start moving upwards again.
So has it got something to do with like the initial velocity being like greater, so it's gonna take longer to turn it around? Does that make sense?
So if we think about opening the parachute, that maybe just say you were travelling at 40 metres a second, and then you are going to reach terminal velocity travelling at 10 metres a second down, then you've decelerated, haven't you? You're going slower than you were before.
Mm-hmm.
And that's because the force vector is up, because
Yep.
you were moving down.
So the terminal velocity vector diagram that we draw for that will look exactly the same as the one that we had before the parachute.
Yeah.
And we only really know that it's travelling at a slower speed because of the information that we've been given. Sort of.
Yes. Yeah, that's right. Because these are force vectors, aren't they? And so we're not talking about velocity vectors. The velocity will change. But here, if we are decelerating, if we're travelling 40 metres a second down, and then after the parachute we end up at a terminal velocity of 10 metres a second down, then we have decelerated. And that means that the vector acting up has to be bigger than, in total, must be bigger than the vector acting down. Okay? Does that make sense? All right, very good. It's hard stuff.